Hey everyone, welcome to this explainer. Okay, we are diving straight into a truly massive breakthrough in AI architecture today. We're going to explore how modern vision language models finally, and I mean finally, learn to process real-world images properly. We are talking about the massive shift from forcing absolutely everything into tiny, distorted boxes to actually processing visual data at its true native resolution, all without completely blowing up our compute budgets. For years, AI developers operated under this incredibly restrictive assumption. They were trying to force the entire visual world into these perfect little tiny boxes. But the fundamental truth we all know is that real images are simply not 224 by 224 pixel squares. The real world just doesn't cooperate with that dimension, right? I mean, just think about the extreme difference between a tall, narrow receipt that you might scan on your phone, which usually sits at around a 1:3 ratio, and a massive widescreen medical scan or a really complex data chart at 16 by 9. When your underlying model expects a perfect square, you have this major fundamental structural conflict between the data you actually have and the data your model can actually eat. So here is our roadmap for today. We're going to hit point 1, the resolution problem, 2, the patch and pack revolution, 3, the AnyRes toolbox, 4, the block diagonal mask, and wrap up with 5, token budget strategies. Let's get right into it.
All right, part 1, the resolution problem, or basically why the pre-2024 era failed. Let's take a quick look back at the painful compromises from the dark ages of vision language models. Previously, we were stuck with 3 fatal options, and honestly, none of them were good. Option 1, you resize the image to a fixed square, but that squishes the image, it distorts faces, and it entirely destroys the tiny text you need for optical character recognition. Option 2, you crop it to a fixed aspect ratio. Sure, the text isn't squished anymore, but you are literally throwing away most of the actual image data. Plus, figuring out the right spot to crop is a whole separate vision problem in itself. And then option 3, pad the image to its longest side. That fixes the distortion, but because of how quadratic attention costs work, you end up wasting 50% or more of your expensive compute tokens processing absolute, literal empty space. Which brings us to part 2, the patch and pack revolution. This is the paradigm shift that finally got us unstuck. The core mechanism for this whole breakthrough came from Google's 2023 NaVit paper. It showed us exactly how to flatten and pack variable length patches from totally different images into one single sequence. Imagine taking a 336 square image, a 224 square image, and then a wide 448 by 336 image. Instead of catting them all out with zeros to match, you just extract their patches, flatten them all out, and concatenate them right into one long sequence for the batch. Boom! You are completely eliminating ways to compute. Absolutely no padding required. Part 3, the AnyRes toolbox. With that concept proven, let's open up the toolbox and evaluate 3 cutting-edge architectures that are solving this exact puzzle right now. First up is AnyRes, which you've probably seen used in Lava Next. This approach basically brute forces the problem. Given a high-resolution image, it dynamically tiles the image into a grid, like a 2x2 or 1x3 layout, whatever best fits the original aspect ratio. Each of those tiles is processed and then adds a fully resized thumbnail of the whole image on top. So the model gets the best of both worlds. It sees the really high-fidelity local details in the tiles and the global context from the thumbnail perfectly. But, wait for it, there is a massive catch with AnyRes. It is unbelievably expensive. If you take a 1344 by 1344 image and process it on a 4x4 grid, your token count explodes to roughly 9,800 tokens. To put that into perspective for a second, that single image fills up almost the absolute entirety of an 8K LLM context window. It's super effective for sure, but it will absolutely devour your compute budget. Next up, we have MRope, pioneered by QWVL. Honestly, this is a far more elegant native solution. Instead of multiplying your tokens with all that tile and thumbnail overhead, MRope uses 3D coordinates for time, row, and column to process dynamic native resolutions smoothly. You just feed it any height and width, the embedder produces the tokens, and the rotary position embedding rotates the attention using those precise 3D coordinates. It completely drops the need for rigid absolute positional tables. A real game changer. And finally, we have NaFlex from the brand new SIGLIP 2 architecture. This one is all about incredible versatility. NaFlex lets you use a single train checkpoint, but allows you to dynamically pick your token budget right at inference time, based on whatever the task is. Doing a simple semantic retrieval? Just tell it to use 256 tokens. Need to read a highly complex chart? Bump it all the way up to 1,024 tokens. One model, total flexibility, and 0 retraining required.
Moving right along to part 4, the block diagonal mask. Let's get into the weeds just a bit and see how we actually engineer the pack under the hood.
So here's the crucial question. If you pack patches from 3 totally different images into one continuous sequence, how does the model know not to accidentally mix them up? Well, you could build a dense block diagonal mask, which is basically just a giant grid of ones and zeros, making sure image A only attends to image A and image B only attends to image B. But there's actually a much, much better way. Modern implementations use flash attention's cumulative length tensor, or Q sequence. This variable length path skips the dense mask entirely and routes attention directly within the sequence boundaries. In your typical batches, doing it this way is about 10 times faster.
All right, bringing it home with part 5, token budget strategies. Because nobody wants a silent 10x token blowup killing their latency in production, right? Based on the task at hand, here is your essential cheat sheet. If you are sizing a VLM for a product, you have to allocate based on actual content density. Doing heavy OCR or reading dense documents, you're going to need 1024 to 4096 tokens. You'll want NaFlex or AnyRes for this. For charts and user interfaces, 729 to 1024 tokens is really the sweet spot, making Quen's dynamic resolution perfect. For standard natural photos, honestly, 256 to 576 tokens is plenty. The LLM will see more than enough. And for video, you need to aggressively spatially pool that down to just 64 to 128 tokens per frame, running at maybe 2 to 8 frames per second. The rule of thumb, you only pay for tokens where the content density actually demands it.
And that brings us to our ultimate takeaway. I want to leave you with this absolutely crucial, forward-looking 2026 production rule to keep your models fast, accurate, and cheap. Here it is. Pick a max pixels cap based on your specific task. Encode the image at its native aspect ratio right up to that exact cap, pack your heterogeneous batches together, and finally, say goodbye to padding forever. Think about it. If our models no longer have to squish the world into tiny little boxes just to understand it, what kind of unseen details are they going to uncover next? Thanks so much for joining me on this explainer, and keep exploring.